Here we have problem set 30. This is going to be about limiting reactants and percent yield, and we're going to use a lot of the stuff that we learned in problem set 29 about stoichiometry, and this is kind of some of the applications of stoichiometry, and we'll use those skills. So first off, each of the pairs of images below contains substances composed of two elements, X and Y. Identify the limiting reactant, write the balanced chemical equation describing the reaction taking place in each pair of images. Okay, so for this first one, we see that we have X and Y separate, and we make an X with two Y's. So I'm going to say X, Y, 2. Okay, so this is an X and two Y's, so that would be X, Y, 2, and these are individual. Okay, and so to balance that, we're going to need two Y's. Okay, but now we're trying to figure out which one is limiting. So basically, in this case, for every one red, we need two blue, right? So there, that can make one molecule. That could make one molecule. That could make one molecule. That could make one molecule. And I've got red, or X, left over. What that means is Y was limiting. Okay, because my Y ran out, and that's what stopped me from being able to make any more molecules. Y was the limiting reactant. You'll also hear it called limiting reagent. They mean the same thing. So what this is getting at is you would get all this stuff, plus you would get an X, is what this is kind of getting at there. Okay, so here we have X2s and we have Y2s, and we're going to make XYs, and to balance that, we need a 2 there. Okay, so here we've got, there's one molecule, there's another molecule, we've got another, and we have this red, which is X. We have X left over. Because X is left over, our limiting was Y2. That was the limiting molecule, okay, because we have X2 left over. Okay, here we've got X2s and Y2s making XY2s, right? Yep. And so to balance that, we got two X's, so we'll need two X's, and now we have four Y's, so we get four Y's. So let's see, when I do this, I'm going to get, that's going to make one molecule, that's going to make another molecule, that's going to make another molecule, that's going to make another molecule. And I have Y's left over, because Y's are left over. My limiting is X2. And so this is left with 2Y2 is left over. Oh, wait. Hold on. X2 is left over, so my limiting is Y2. And I have two X2s left over. There we go. Okay, this last one, it looks like I have XY2s, and I'm adding X2s, and I'm getting X2Y2. So to balance this, two Y's, but I've got 1, 2, 3 X's and only 2 X's there. So multiply that by 2 and multiply that by 2. So now I have 4 X's, 4 X's, 4 Y's, 4 Y's. Perfect. Okay. Now, these could make a molecule. Those could make a molecule. And that could make a molecule. So what do I have left over? I have x2 left, a little bit of x2 left over, which means my limiting was the x, y, 2. So we're left with 1/2 x2 at the end. Okay, little introduction to limiting reactants, and we'll see how we do this with actual chemistry. But first, another little example. A recipe for 1 cup of hollandaise sauce calls for 1/2 cup of butter, 1/4 cup of hot water, 4 egg yolks, and the juice of a medium-sized lemon. How many cups of sauce can be made from 2 cups of butter, a dozen eggs, 4 medium-sized lemons, and an unlimited supply of hot water? What is a limiting reactant, and what will you have left over if you make the maximum amount of hollandaise sauce possible? Okay, let's talk about how I think about doing this. We have a certain amount of each of our inputs, and we know how much input it takes to make hollandaise sauce. So we could calculate with each of our inputs how much hollandaise sauce could we make, assuming we had unlimited everything else. So let's do that. So we have 2 cups of butter, and you need 1 cup. So butter, 1 cup of hollandaise sauce takes 1/2 cup of butter. So if I have 2 cups, that can make 4 cups of sauce. I have a dozen eggs, and I need 4 eggs to make a cup. So my eggs could make 3 cups of hollandaise sauce. I have 4 medium-sized lemons, and 1 medium-sized lemon makes 1 cup. So my lemons could make 4 cups. I have unlimited supply of hot water, so that can make my water could make as many cups as I want. Okay, what's the limiting reactant? What is limiting the amount of stuff I can make? It's the eggs, because the eggs can make the least. Okay, we're gonna make, once we make 3 cups of hollandaise sauce, we're out of eggs. We still have everything else left over. What will you have left over if you make the maximum amount of hollandaise sauce? Well, after I make 3 cups of hollandaise sauce, I'm gonna have 1/2 cup of butter left. Okay, and that's because there's 1 cup's worth of hollandaise sauce that I didn't make, and that 1 cup would be 1/2 cup of butter. So that's why I have 1/2 cup of butter left. I have 0 eggs left because I used them all up. Lemons, I have 1 lemon left, and I still have unlimited water. Okay. And you'll see how that applies as we do some further limiting reactant problems. All right. 1 liter of seawater. A 1 liter sample of seawater contains that much chloride, that much sodium, and that much magnesium. How many moles of each ion are present? Well, they give me grams of the ions, so let's get them to moles. I think it's 35.5. Yep. Oh, 0.547 moles. Cl minus. 10.8 grams. Sodium plus. Sodium weighs 23. So that's 0.47 moles of Na plus. And lastly, my 1.29 grams of magnesium. And magnesium weighs 24.3 grams per mole, which gives me 0.0531. So I just took each of those grams and converted to moles. Nothing too spectacular there. If the seawater were evaporated, would there be enough chloride ions present to form the chloride salts of all the sodium and magnesium ions present? Okay, so basically, we know that the cations are going to attach with anions, right? So I'm going to get the Na connecting with Cl, and I'm going to make some NaCl when the water evaporates. I'm also going to get the Cl connecting with magnesium. That's going to make MgCl2, right, because of the charges. So I'm trying to see if everything evaporates, do I have enough chlorine to pair up all of these ions, or will there be some ions remain? There's a couple of ways of approaching this problem. What I'm going to do is I'm going to say, with all of my moles of sodium and moles of magnesium, how much chlorine would I need to match them all up? Okay, and I know that of my 0.470 moles of sodium, this molecule tells me that for each mole of sodium, I need 1 mole of Cl minus. So if I wanted to match all the sodium up, I would need 0.47 moles of chloride. Magnesium, I have 0.0531 moles. And for each of those moles of magnesium, I would need 2 moles of Cl minus. Now, obviously, there's like very intuitive ways. You don't have to write it out the way I've written it out this way. But that would then require me to have 0.106 moles of Cl minus, which means I would need 0.576 moles of Cl minus total, and I have 0.547. So do I have enough to match everything up? I do not. So would there be enough chloride ions present to form the chloride salts of all the sodium and magnesium? Nope, there would not, because I need 570 or 0.576 moles, and I only have 0.547 moles. Sweet. All right, silver nitrate is used to plate objects with silver. You learned in your favorite chemistry class that silver metal and zinc nitrate are produced when zinc metal is placed in a solution of silver nitrate. So zinc metal is put in a solution of silver nitrate, and it makes silver metal and zinc nitrate. You decide to apply this knowledge by attempting to plate your favorite spoon of silver. This is not how it's actually done. You put your spoon along with 2 grams of zinc into a solution of silver nitrate containing that much silver nitrate. Write the balanced equation. Okay, so we know we've got zinc plus a solution of silver nitrate. Okay, and this is, I'm just going to say this is aqueous. The zinc is solid. And that's going to make my products here silver metal, and zinc, which is a 2+. Now to balance this, I'm going to need 2 of those, 2 of those. Okay, so I have my balanced equation. Which reactant will run out first? Okay, so the idea here is if we just give you the amount of a single reactant, if I just said you have this much zinc, then how much silver do you make? Well, then you would just assume that you have an unlimited amount of silver nitrate, and you just use the coefficients to convert between zinc and silver, as we talked about in problem set 29. But in this case, I'm saying you've got 2 grams of zinc and 2.5 grams of silver nitrate. Anytime you're given amounts of both reactants or more than one reactant, one of them is going to be limiting. And it's that limiting reactant that defines the entire reaction and how much is going to happen, right? Because once it runs out, everything stops. Kind of like this hollandaise sauce example. Once we ran out of eggs, everything stopped. So the eggs determined everything about the reaction. Well, here, we've got to figure out which reactant is going to run out first, because that's going to determine everything about the reaction. And just like with the hollandaise sauce, the way we figured that out was we took each of our reactants and said, how much product can I make with that reactant? And whichever reactant made the least amount of product, that's going to run out first. We're going to do the exact same thing here. I'm going to take my two reactants, I'm going to pick a product, and whichever one makes less of that product is limiting. And here's just a trick. I'm going to look at the next problem. It asks how many grams of silver will be formed. So I'm going to pick silver as my product. I could convert to either of these. I'm going to pick silver. All right, so I've got 2 grams of zinc. I'm going to figure out how much silver it makes. 1 mole of zinc weighs 65.4 grams. Reaction tells me 1 mole of zinc makes 2 moles of silver. And we're trying to get grams, so 1 mole of silver weighs 107.9. All right, 2. That gives me 6.599 grams of silver. Okay, now I'm going to figure out how much silver I get from my silver nitrate, which I have 2.5 grams of. Molar mass of AgNO3 is going to be 107.9 plus N plus 3 O's. Give me 169.9. My reaction tells me that 2 moles of silver nitrate make 2 moles of silver, and 1 mole of silver is 107.9 grams. So that tells me I got 1.588 grams of silver. Okay, so my zinc, if I used all my zinc, I'd get 6.599 grams of silver. If I use all my silver nitrate, I get 1.588 grams of silver. So how much silver am I going to make? I'm going to make 1.588 grams, and that's really the answer to this question. Because my two reactants react, and once 1.588 grams of silver is made, my silver nitrate runs out. It's gone, and so the reaction stops. I never get this much. This number doesn't mean anything. It never happens. It's just how much, if you had zinc and an unlimited amount of silver nitrate, that's how much silver you would make. But that number doesn't really mean anything. So the question now is, which reaction will run out first? AgNO3 runs out first. AgNO3, because it makes less silver. Okay, so I've run my reaction. Now everything is based off AgNO3. If the problem asked how much zinc nitrate is made, I wouldn't have to do this double process again, because I know AgNO3 is my limiting reactant. So I would just take my AgNO3 and convert it to zinc nitrate. Okay, assuming this amount of silver is sufficient to plate the spoon. So we run this reaction just like this, and then the spoon is plated. How many grams of each reactant will it take to replenish your setup and plate another spoon? Okay. I'm going to draw a picture. This is my zinc. This is my silver nitrate. I run my reaction. At the end of the day, silver nitrate was the limiting reactant, and so it's all gone. My zinc, however, I lose it. I don't know how much I lose, but at the end of the day, it's not gone. If it was gone, I would have made 6.599 grams of silver. It's not all gone, which means there's still some left. Okay, and we've got to figure out, if we want to run this reaction again, how much of each reaction do we have to add? Well, silver nitrate's easy, right? It's gone. So if I wanted to run the reaction again, I would have to add the same amount of silver nitrate that I started with. I'd have to put back in 2.5 grams of silver nitrate, okay, because that's all gone. Now I got to figure out how much zinc would I have to put back. Well, that depends on how much I used and how much I still have left in there. So this is my favorite way of working this out. I've got 2.5 grams of silver nitrate. That defines the reaction. If I convert that to a product, it tells me how much product I would make with that amount of silver nitrate. But if I take that silver nitrate, that 2.5, and convert it to zinc, the other reactant, it tells me how much zinc I used up reacting that silver nitrate. Okay, so let's do that. So if I take my 2.5 grams of silver nitrate, I'm going to convert it to zinc, the other reactant. Two moles of AgNO3 make 1 mole of zinc, and 1 mole of zinc weighs 65.4 grams. All right, that tells me 0.481 grams of zinc. All right, so I've taken my silver nitrate, one of my reactants, and I converted it to zinc, which is the other reactant. Now my limiting reactant defines the reaction. So AgNO3, that 2.5 grams, defines how much products I make and how much of the reactants I use. So take that 2.5 grams, I convert it to zinc, and that tells me that I used 0.481 grams of zinc. Well, how much did I start with? I started with 2. So 0.481, that's like a little less than a quarter. Right, so this whole thing is 2.5 or 2.0. This is 0.481 grams. All right, so if I want to run this reaction again, do I need to put those 4.481 grams back in? No, because I still have plenty left, more than 0.481. So I don't need to add any more zinc in there. I've got enough to run this reaction at least 3 more times. So I have to add 0 grams of zinc and 2.5 grams of silver nitrate. All right, hopefully we'll get some opportunities to do more of that. So let's keep going. Number 5. Suppose 75 metric tons of coal, that is 3% sulfur by mass, is burned at a power plant. During combustion, the sulfur is converted to SO2. So I've got my sulfur, and I burn it, and I get SO2. Anti-pollution scrubbers installed in the smokestacks of the power plant capture 3.9 metric tons of this SO2. How efficient are the scrubbers in capturing SO2? How many metric tons of SO2 escaped? Okay, so we're burning 75 metric tons of coal, and it's that much sulfur. Well, that sulfur is going to be converted into SO2, okay, and then our scrubbers catch that much of it. But some of it's escaping, which means we're going to end up we're going to make more than 3.9 metric tons of SO2. We got to figure out how much we're going to make to figure out what percent we catch and what gets out. All right, so I've got 75 metric tons of coal, but coal is not in this equation. I'm burning the coal, but this reaction is about the sulfur. And so I'm just going to quickly take my 75 metric tons and get the 3% of it, which is 2.25. So I got 2.25 tons of sulfur. That's my starting value. I got to find out how much SO2 that's going to make when we burn it. 2.25 tons of sulfur. Okay. If you don't know, 1 ton is 1,000 kilograms. 1 kilogram is 1,000 grams. And 1 mole of sulfur weighs 32 grams. Well, now this equation is balanced, so I know 1 mole of sulfur makes 1 mole of SO2. Go to grams, so 32 plus 2 oxygens is another 32, so 64. Okay, and now I want to get to metric tons, right? So grams, and then I know 1,000 grams of SO2 is 1 kilogram, and 1,000 kilograms is 1 ton. Okay, that line a better length. All right, now I'm getting tons of SO2 from this reaction. Okay, 2.25. And I got 4.5 tons of SO2. That's how much SO2 I'm making by burning this coal. Now the scrubbers are catching 3.9 metric tons. So how efficient are they? You know, there's different ways to answer this question. I'm going to put this efficiency as like a percentage. So my efficiency is going to be the 3.9 that I caught divided by the 4.5 that I made, that I should have caught. And 3.9 divided by 4.5, 0.867. So 86.7% efficient. And then I ask how many metric tons escaped? Well, that would just be the 4.5 that I made minus the 3.9 that I caught. So 0.6 tons escaped. There we go. All right, number 6. Baking soda is produced on an industrial scale by the Solvay process. A reaction in the process is this guy. Suppose a reaction vessel initially contained 58.5 kilograms of NaCl, 18.8 kilograms of ammonia. And excess CO2 and water. So excess, that just means we have more than enough. So we know CO2 and water are not going to limit our reaction. We make 66 kilograms of NaHCO3. What's the percent yield? All right, well, percent yield is defined as our actual amount that we actually got, so that 66 is what we actually got, divided by our theoretical amount that we could have gotten. Our theoretical is, like, mathematically, what's the maximum we could have gotten based on what we started with. So we have the actual for our percent yield. We need the theoretical. And again, the theoretical is mathematically how much could we make. So we're trying to figure out, based on what they give us, how much NaHCO3 could we make. Okay, the problem is they give us amounts of 2 reactants. Well, if they give us amounts of 2 reactants, we know one of them is going to be limiting. And so we have to run the math with both of them to see which one makes less of that product that we care about. So we're going to go ahead and do that. So got to get to moles so that I can use my equation. 1 mole of NaCl is going to be 23 plus Cl is 35.5, 58.5. It's the molar mass of NaCl. Okay, my reaction, looks like the reaction is balanced. Yep. Yeah, pretty sure yes, it's balanced. Okay, so we can then say that 1 mole of NaCl makes 1 mole of NaHCO3. Okay, but they give us an amount in kilograms, so let's get all the way up to kilograms. Molar mass of NaHCO3. NaHCO3. And I got 84. And there's 1,000 grams in 1 kilogram. All right. And that tells me that I can make, for my NaCl, I can make 83.57 kilograms of NaHCO3. Okay, but I don't know if I'm going to make that much because I don't know if NaCl is going to run out before or after the NH3. So I've got to do the same thing with NH3. Okay. And that gives me hold on. Oh, did that wrong. Okay. That gives me 92.89 kilograms of NaHCO3. Okay, so I look at this. They give me both reactants. So in order to figure out which one was limiting and therefore which one defines the reaction, I converted both of them to a product. Okay, and we see my NaCl makes less product, and therefore NaCl is limiting. Okay, so this is the amount of product that I make, not this. Okay, so then I'm trying to find my percent yield. Well, percent yield is my actual over my theoretical. Actual is 66, theoretical is 83.57. And that gives me about 79% yield. Okay. So this mixed a couple of things, namely the percent yield idea with the limiting reactant idea. All right. An industrial process for producing hydrogen gas is based on the reaction between steam and carbon emitted to incandescence, heated to incandescence, producing a mixture of CO and H2 called synthesis gas or syngas. Write a balanced chemical equation describing the production of syngas. Okay, between steam is gas, water, and carbon. I'm going to just guess that carbon is solid. Producing CO gas and H2 gas. Looks like it's already balanced. If a reaction vessel that initially contains 66 kilograms of carbon and excess steam produces 6.8 kilograms of hydrogen, what's the percent yield? Okay, so again, percent yields are actual over our theoretical. They tell us how much we actually make. So I got my actual, I need my theoretical. Theoretical is based on math, and the math is going to be how much H2 can I make with the carbon that I have. And seeing as they only give me one reactant, there's no limiting reactant issue. Here we know carbon's limiting reactant because I have excess steam. So I got to just change my carbon into hydrogen. And lastly, get it into kilograms. And that's going to give me 66. That's going to give me 11 kilograms of H2 that if all of my carbon reacted perfectly and I captured all of it, I would get 11 kilograms of hydrogen. Okay, but it didn't because I only got 6.8 kilograms, so my percent yield is going to be that 6.8 divided by 11, which gives me 61.8% yield. All right. Commercial manufacturers produce nitric acid by the Ostwald process. The process requires 3 steps. No, they're all balanced. Beginning with 37 kilograms of ammonium and an unlimited supply of oxygen and water, how many kilograms of oxygen gas will be consumed in the process? Okay. So we're consuming oxygen in 2 steps, step 1 and step 2. So if we want to find the total amount of oxygen, we need to figure out how much oxygen do we consume in step 1, how much oxygen do we consume in step 2. We have to add those together. Okay, well, we start off with our 37 kilograms of ammonia. And we got to get it. Let's do step 1 first. Now, some of you might have noticed that a lot of this time we're converting from kilograms into grams and then back into kilograms on the back end of the problem, and those things just cancel each other out. So if you recognize that and you want to take a shortcut, go for it, but I'm going to write the whole thing out. In that first step, we end up using 87 kilograms of O2. In the second step, a lot of these are going to look the same. All right, I'm trying to get to this guy. Well, I can't go 4 to 1 because these 3 equations are not balanced together. Okay, each equation is balanced on its own. So what I have to do is I have to jump. So I look for something in the second reaction that's also in the first. So I'm going to take my NH3 and convert it to NO. So 4 moles of NH3 makes 4 moles of NO. And then I say, well, now I got NO and O2. So 2 moles of NO makes 1 mole of O2. Then I can get that out to my kilograms. And that gives me 34.8 kilograms of O2. So how much total is used? It's my 87 plus 34.8, which looks like 121.8 kilograms of oxygen used to burn to react all of my ammonia. Part B, how many kilograms of nitric acid will be produced? All right, so I've got my 32 kilograms of ammonia, and I'm trying to get to nitric acid. Well, this is going to be a 3-step process. Ammonia to NO, NO to NO2, NO2 to HNO3. Okay, starting with my 37, is that right, 37? Yeah, 37 kilograms of ammonia. Okay, so we've got 4NH3 to 4NO. And then we've got 2NO to 2NO2. And we've got 3NO2 to 2HNO3. Wait. Yep. And now I got to get that out to kilograms. HNO3 is 63. And then of course there's 1,000 grams in 1 kilogram. All right, all that math gets us 91.4 kilograms of nitric acid. That's how much theoretically I could make with my 37 kilograms of ammonia. All right, if the process actually had a percent yield of 83%, how many kilograms of nitric acid would actually be produced? All right, so my 83%, make that a decimal, that's equal to my actual, which is what I'm looking for, over my theoretical, which is that 91.4 that I just found. Okay, so multiplying the 91.4 over gives me an actual yield of 75.86 kilograms. That's just the percent yield equation used backwards. Okay, pound for pound, there's more sulfuric acid. More sulfuric acid is produced in the world than any other chemical. Another 3-step process. If you started with 25 kilograms of sulfur and unlimited oxygen and water, how many kilograms of sulfuric acid would be formed at 100% completion? So I start with my 25 kilograms of sulfur. And again, 1 kilogram, 1,000 grams. 1 mole of sulfur weighs 32. And this reaction says 1 mole of sulfur makes 1 mole of SO2. Two moles of SO2 make 2 moles of SO3, and 1 mole of SO3 makes 1 mole of H2SO4. Okay, but I'm trying to get to kilograms, so 1 mole of H2SO4 is going to weigh 98. Yep, 98 grams of H2SO4 and 1,000 grams in 1 kilogram. All right, so that gets me 76.56 kilograms of sulfuric acid from 25 kilograms of sulfur, as well as a bunch of water and oxygen. In real life, formation of sulfuric acid is an equilibrium process in which the reaction does not go to completion. If you obtain 54.36 kilograms of sulfuric acid, what's the percent yield? Again, percent yield is going to be my actual, which was that 54.36 divided by my theoretical. You have to make sure these are the same units. In this case, both are kilograms. And that gets me a percent yield of 71%. Okay, how we looking? Couple left, 3 left. All right, use the following reaction. Assume excess carbon monoxide. You start with 16 grams of iron 3 oxide and produce 8.4 grams of iron metal. What's the percent yield? Percent yield is actual over theoretical. They give us the actual. Let's find the theoretical. Now I get to moles to use the equation. Molar mass of iron 3 oxide. Fe is 55.85 plus 3 oxygens. It's me 159.7. The reaction tells me that 1 mole of Fe2O3 makes 2 moles of Fe. And then I know that 1 mole of Fe weighs, what was it, 55.85 grams. So theoretically, with my 16 grams of iron 3 oxide, I could make 11.2 grams of iron. So then my percent yield is going to be my actual of 8.4 over my theoretical of 11.2, which gives me 75, I should say 75% yield. Convert that decimal into a percent. All right. Next it asks, if you wanted to produce 100 grams of iron metal and you knew that the percent yield was 80%, how much iron 3 oxide would you need to start with? All right, so I want this to be my actual iron, and I know my percent yield is 80%, 0.80. And I want to get 100. How much do I theoretically have to aim for in order to get 100 grams? Well, if I do this math, rearrange it, I get that the theoretical is going to be 100 divided by 0.80, and that's 125 grams of iron. In other words, if I want to walk away with 100 grams, I need to shoot to make 125 grams because I know that I'm only going to get 80% yield. So I'm going to get less than at 125. I'm going to shoot for 125 to get 100. Now I have to say, well, how much iron 3 oxide do you need to start with? Well, I'm trying to get 125 grams of iron. So I'm going to convert this back from iron to iron 3 oxide to figure out how much I would start with to get 120 to try and get 125 grams. Molar mass of iron. The reaction tells me 2 moles of iron come from 1 mole of Fe2O3, and that 1 mole of Fe2O3 is 159.7 grams. So if I'm going to aim for 125 grams of iron, I need to start with 178.7 grams of Fe2O3. Okay, I'm going to start with 178.7 grams of Fe2O3. I'm going to convert it into iron, which would theoretically make 125 grams, but I only get 80% yield. And so I'm actually going to get 100 grams, which is what I want to produce based on the problem. So a lot of these percent yields, just working forward and backward is what we're doing over and over here. All right, 185 grams of iron 2 oxide react with 38 grams of aluminum based on this reaction. What is the limiting reactant? All right, because they give us amounts of two reactants. They give us 185 grams of this, and they give us 38 grams of this. And they ask what's limiting. How do we figure out what's limiting? We're going to convert each reactant into one of my products, okay, and whichever one makes less product is limiting. And to figure out which product I want to use, I'm going to look at the next part of the problem. It says how many grams of total product are formed. So they want us to eventually find both, so we can pick either product. Let's pick Al2O3. All right, so I'm going to convert my FeO, 185 grams of FeO, 1 mole of FeO is 55.85 plus 16, 71.85 grams of FeO. The reaction tells me that 3 moles of FeO make 1 mole of Al2O3, and then the molar mass, 1 mole of Al2O3 weighs 2 aluminums, 27 times 2 plus 3 oxygens. That's 102, I believe. Yeah, 102 grams of Al2O3 per mole. So my 185 grams of FeO could make, is that right? No. Okay. Eighty-seven 87.54 grams of Al2O3 is what I got there. Okay, so now I'm going to do the same thing with my 38 grams of aluminum. 1 mole of aluminum is, I know I just figured this out, but I lost it, 27 grams of aluminum, and 2 moles of aluminum from my reaction make 1 mole of Al2O3, and then 1 mole of Al2O3 weighs 102 grams. So my aluminum could potentially make 71.8 grams of Al2O3. All right, so which is going to be limiting? Well, my aluminum makes less, so aluminum is my limiting reactant. Okay. Do we ever make 87 grams of aluminum oxide? Nope, we don't, because once I make 71.8, I run out of aluminum, and so the reaction stops. How many grams of total product formed if the reaction goes to completion? All right, well, we already know how much Al2O3 we get, 71.8 grams, because that's based off our limiting reactant. Now we need to figure out how much iron do we get. Again, it's going to be based off our limiting reactant, which is aluminum. So let's take our 38 grams of aluminum. Let's convert that into iron. That's a 2:3 ratio. And 1 mole of iron is 55.85. So how much iron do I get? $118 grams. Okay, now you might wonder, well, could I take my FeO and convert it to iron as well? And you could. You'll just find out that it makes more iron than the aluminum, so you're going to use the lower number anyway. Okay, so how much total product? 71.8 plus 118 gives me 189.8 grams. That's the real answer to that problem, to this question. All right, the total mass of the reactants is 223. However, this is not the total mass of the products. Why not? So what this is getting at is the law of conservation of mass, right? We say, based on the law of conservation of mass, when I run a reaction, I need to start, whatever amount of stuff I start with, I'm going to end with that same mass of stuff. So why is it that the products weigh 189.8 grams, whereas the reactants weighed 223? It's almost as if mass was lost. Well, that's not the case. Because the law of conservation of mass says what I start with is the same as what I end with. It doesn't say that all the reactants I start with is the same as all the products I end with. Okay, because if you think aluminum was my limiting reactant, it ran out, so these 38 grams got completely turned into products. But my FeO did not run out. So at the beginning of the day, you've got 223 grams, right? At the end, and it's all aluminum and iron oxide. At the end of the day, you're still going to have 223 grams. You're going to have 189.8 grams of this stuff, and the rest of it's going to be iron oxide that was left over. So the real key here is that iron oxide, I guess iron to oxide, doesn't all react. So you have some remaining. After the reaction. So you haven't lost mass. It's just not all of your reactant mass got turned into products. All right, if the actual yield is 105 grams of iron, what's the percent yield of iron? Okay, well, the percent yield is my actual, which was 105, divided by my theoretical, which, okay. My theoretical was 118 for iron. Make sure they're the same units, both grams here. And that gets me, I got 89%. Okay, last one. In a manufacturing process, gas A reacts with gas B to form gas C, according to the following equation. You've got 7 liters of A, 2.7 liters of B. How many liters of C can you make? Well, they give you 2 reactants, so that means you're going to have a limiting reactant here, so we've got to see how much C each of my reactants can make. And if you remember, usually we have to get into moles to use a balanced equation, but if we're using all gases at constant temperature and pressure, we can use these molar ratios 3:1:2 as volume ratios, and so I can just say 7 liters of A. The reaction tells me that 3 liters of A makes 2 liters of C, which gives me 4.67, I think, liters of C. Okay, and then 2.7 liters of B, and the reaction tells me 1 liter of B makes 2 liters of C, which gives me 5.4 liters of C. So how much can I actually make? Well, I'm actually just going to make 4.67 because my A is going to run out before my B does. If you isolate 3.14 grams of gas carbon at STP from the reaction part A, what is the molecular weight of C? All right, so they tell us this 4.6 liters, that's my volume. That weighs 3.14 grams is my mass. I'm trying to find the molecular weight. Well, remember, molecular weight is grams per mole. Well, there's my grams. I just need to get my moles. And since I have a volume and a temperature and a pressure, I can get moles. Moles is going to be PV over RT, which standard pressure is 1 atmosphere. Not standard volume. The volume I get is 4.67 from part A. R, 0.08206. And T, standard temperature, is 273. So that gives me 0.208 moles of gas C. So my 0.208 moles weighs 3.14 grams, so my molecular weight is going to be 0.208 grams per mole. So 3.14 grams divided by 0.208 moles. Which gets me a molar mass of 15.1 grams per mole. So I gave the grams they gave me. I took the grams they gave me, and I found the moles from my volume, temperature, and pressure using the ideal gas law, and then I just said grams divided by moles gives me my molar mass. All right, what a problem set. Okay, hopefully you felt good about this, and you felt like you got plenty of practice, and you understand the function of limiting reactants and how to do math associated with it, as well as percent yields.